So for day 15, we've got a sensor and beacon problem. This reminded me of another problem from last year's Advent of Code that used sensors and beacons, which was a very challenging problem. This one is not quite as challenging, and yet I still managed to screw it up. So we'll go through the wrong approach I tried, and then we'll look at the correct approach for this problem. So what we have here is a list of sensors, and each sensor has a corresponding beacon. All of these are just locations. So the sensor tells us what the closest beacon is by Manhattan distance, so we're in a 2D grid here. So what this means is that, so the problem we are trying to solve, though, is that we know a distress signal is coming from a beacon, but it's not one of these beacons, which means we want to determine where the distress signal is coming from, but it's not one of these beacons, and so, but there's a rule that allows us to exclude places where it could be, and ultimately we'll narrow down the location by excluding every possible location. How do we exclude locations? Well, let's consider this sensor. So I think we're dealing with this sensor. So we know that the sensor's closest beacon is here. And that means that the distress signal beacon that we're trying to find cannot be closer to this sensor than this beacon. That means we can exclude all of these locations from containing the distress signal. And we can do that with all of these sensors, and we can potentially exclude a very large number of squares. Now, the first part of the problem tells us to only consider a single row, so a single series of y-coordinates. And the y-coordinates are increasing as we go down, the x-coordinates are increasing as we go right. So what does the first part tell us to do? It tells us to pick a specific y-coordinate, a specific row, and just determine how many squares are excluded within that row. Now, what did I do? I looked at the two inputs. I was like, okay, day one, or for the small part, we've got 14 sensors. For the large part, we don't actually have that many sensors. We have 27 sensors. And I said, well, okay, the scale isn't actually that big, so I can just do a breadth first search, accumulate all of the locations that are too close to a sensor to contain the right beacon, and then we can just build up a hash set, and then I'll just filter that hash set to just take the elements that are at the current y value. And I'm thinking to myself, okay, why? This should have been my first clue, is that, well, my approach gives me too much information. I have to filter down that information for part one. It's like, why would that work? And the answer is the solution approach that I just proposed does not work at all for the large thing, because I said, well, the scale isn't that big because it's only 27 sensors, but we have to look at their coordinates. And if you look carefully at how large these coordinates are and how big a difference there is, basically these items span a system from like 0, 0 to like 4 million, 4 million. So we've got a massive search space, and if you're doing a breadth first search from each of these in a very large search space, that's going to take a very long amount of time. And I didn't think about the size of these numbers in determining the scale of the problem and how long that would take. So what is the correct approach to this? Well, we have to think about what did they actually tell us to do. They told us to find just the number of excluded squares in a single row. So let's do that. First, of course, we have to parse this. There's nothing challenging about about parsing this input. It's just a bunch of keywords, and we parse some integers. Nothing is complicated there, because parsec monad is great. So what do we do to solve this? So here's the approach that we're going to take. So process input easy. I'll outline the approach, and then we'll look at the individual functions. So first, we want to get a series of intervals along this row. So when I put size here, this is actually the row number that we're dealing with. It's a smaller row number for the smaller input and a larger row number for the larger input. So I could probably rename this as just row, and it would probably make a bit more sense. That just looks a little better. So first, we're going to take a look. So for all of these sensors, we are going to potentially exclude one interval of locations from that row. Then we're going to merge these intervals together. Then we are going to get all of the beacon locations within that row, and we're going to count the size of the intervals excluding all of those beacons. It sounds a little complicated, but it's a three-step process. So let's do the first step. First, we take a single coordinate and a single combination of sensor beacons. So we have a coordinate for the sensor and a coordinate for the beacon, and we want to determine an interval, potentially an interval of excluded squares. Why does an interval make sense? Well, let's look at this picture again. So we're looking at row 10, and we've got our sensor location. Now, we can calculate the Manhattan distance to the sensor location, and then we can calculate the distance from our sensor to the row in question. Now, of course, if that distance is less than the total distance to the beacon, then we can exclude some of the locations on that row. How many can we exclude? Well, we take the remaining distance. So in this case, I think the Manhattan distance is 9, and it's a distance of 3 from row 7 to row 10. And so we have then 6 in each direction that we can exclude because of this particular sensor. So how does this look in code? Well, we get our distance from the sensor to the beacon, we get the distance to the row, we get our leftover distance. Now, if there is no leftover distance, we just return nothing. There's no interval that we can actually get because there are no excluded squares. I don't even want to deal with the issue of having like a negative interval or anything like that. I'm just going to return nothing. Now, what else can we do if we can actually reach that row? Well, we'll return interval. It starts from just that starting exposition, the sensor exposition, and we go to the left, the amount of the leftover distance, and we go to the right, the amount of the leftover distance. So importantly, this is an inclusive interval that will come into play later, but we'll just return this value. So this calculation, this is totally constant time, which is a very good thing because we're going to, this calculation doesn't depend on the total area that is being covered. It doesn't depend on the size of the Manhattan distance. So we get all of these intervals. So for example, we might get, we'll get this interval from this sensor. This sensor will also give us, a fairly large interval. So on and so forth. This sensor, probably won't give us any intervals, but, we have all these intervals. And now we're going to merge them together because we don't want to be dealing with okay, some of these overlap, they're disjoint, and we have all these things. So let's just merge them together. This incidentally is, this is a good problem to just tackle on its own as an interview problem. I have been asked this problem in interviews, technical interviews in the past, where you just take a series of intervals and basically merge them together, try to find holes and that sort of thing. So this is just a recursive function. If there are no remaining intervals, we just, take our current interval, put it in front of the accumulated intervals and reverse that. That's our base case. In the accumulate case, we have at least one to compare to. And if the start is greater than the current's end, then we have two separate intervals. So we're going to put the current onto the list of the accumulated, treat this first one as our new sort of focus, as our new current interval, and then we'll recurse. And then otherwise, what happens is that we're merging two intervals. So we take the start of the current interval, and then we take the maximum value between these two ends. And we'll make a new interval out of that. That's our new focus interval, and then we recurse just on the rest. So that's how we merge our intervals together. Now the last step is we have to count the number of spaces in these intervals, excluding beacons, and obviously we still want to do this in a way that is not sensitive to how large these numbers are. So we have to be a little bit careful about that. And the other thing is we have to exclude the locations of the beacons themselves. They give us this example with 10, and if we look here, the answer we want in this part is 26, even though this full thing is 27 because we have to exclude this beacon location. And this is a little bit tricky. It's still just, again, a recursive function with a number of base cases, but we have to loop through the intervals. We also have to loop through the beacon X locations. These aren't the full beacon sensor location because we're only considering beacons that are on that row already. So we sort these. Our intervals we assume are sorted. If we run out of more intervals to add, then we can return the accumulated value. So here we're returning an int, we're returning the total size contained by these intervals. And then we have our recursive cases. So if we are out of beacons, then it actually gets a little bit simpler because we just take our next interval and we get the size of that interval. So it's next 2 minus next 1 plus 1 because the intervals are inclusive. And we add that to our previous accumulated count value, and then we just recurse. If we have intervals and beacons remaining, there are a few cases. If the beacon is before our current interval, we can just drop it and recurse on everything. We recurse on all of the intervals and just the rest of the beacons. If it's greater than, if it's beyond the end of our current interval, then again, we just factor in. Wait, did I miss a +1 here? I might have missed a +1 here. Yes, I feel like there is supposed to be a +1 in this case, just like there is here, which means this case might not actually have come up in the two cases they gave me. That's kind of interesting. I'll see if that actually changes my test results. That'd be very interesting if it didn't. Oh, no, I know. This should be more correct. You know, notice that this problem, it takes a little bit. We don't get an instant solution. Okay, so this is probably more correct. I think I missed that +1. But then we recurse, we keep next beacon is greater than next 2. I'm not sure that should have been next beacons. I feel like this should be beacons. I don't think I should exclude next beacon there. This case was very sloppy. Let me see if that changes things. I think most of the cases, we just ended up with one continuous interval, as we'll see in part 2. But yeah, so there are some edge cases that just didn't come up because it turned out that the answer was kind of simple. But yeah, this is kind of interesting. So here we are basically consuming an interval. We're not consuming a beacon in this particular case. Here we're consuming a beacon but not consuming an interval. And in this case, we are consuming a beacon. We are not consuming an interval because the beacon is in between the intervals. So the only difference between this case and this case is that we subtract 1 from our accumulated value, because the beacon takes away one of the spaces that we would otherwise count in that interval. So yeah, this function is definitely a little intricate. Not surprising that I kind of messed up this case a little bit, but again, as we'll see in part 2, most of the time we're just going to be getting one solid interval from all of these rows. So it didn't make a difference. So then to complete part 1 of the problem, we have to get all these intervals, we have to merge them together, we have to get all of the x locations of the beacons. So we have to use nub because we want to deduplicate this list, but take all of the coordinates where the y value is equal to our row. And then we'll run this count intervals excluding beacons. So that gives us our answer for part 1. Part 2, what we want to do, going back here, now we're limiting our search space to a finite area, because previously we were technically dealing with a boundless area that, like, theoretically, the distress beacon could have been outside of our area as far as we knew. But now we're saying, okay, we know the distress beacon is in this area from 0, 0 to 4 million, 4 million, like is that a very large area. But apparently, in spite of that, there is still only one space, a single space, that we have not excluded. So we have to find a hole in the list of intervals, and that's what this find hole function is all about. And obviously, if we have no intervals, we're just, we're not going to return int. This hole that the int we're returning here is the x value. I think, yes. Right? Because we always have a maximum column here. The minimum column is always 0. And I'm trying to remember where the row actually works in here. I guess the interval is always pegged to a particular row. So we'll always be able to find it. But anyways, we have these intervals, and so let's look at this case of the singleton interval. Again, here, if the start of the interval is greater than 0, then we have a hole right before the interval even starts. If the end is less than the maximum column that we're looking for, then we have a hole. Otherwise, there is no hole. That's the singleton case. which is probably the case that actually ends up getting run most often. Now, if we have multiple intervals, the question is, does end 1 and start 2, is there a space between them? If there's a gap between them, then we can return that gap. Otherwise, we have to recurse. I probably could have written my merge function so that I could exclude this case. This case where there's no gap between n1 and start 2. I didn't think about that, but oh well. I think this nonetheless still works. So what we do here is we evaluate an individual row. So we do the same thing where we get the intervals for that row, we merge them together, and now we try to find the hole in that interval. So this gives us the column, the x, or I guess the x coordinate. And if we don't find that, then we recurse. We do this potentially for all 4 million rows. So it's recursive, and it says, like, okay, if I don't find it row 0, I'm going to try row 1. That's what this recursive case is doing. Because the reason we do it that way rather than a map is because, we want to short circuit if we get the answer. We don't want to keep going because we only need one answer. And of course, if we get the column, if we get the hole, then we'll just return column together with the row. Okay, that's where the row is factored in there, and that's going to give us the coordinate. And so for our solution, we just have to multiply by 4 million and the column by 4 million and add the row, and we get our answer. So that is the solution for day 15. It's definitely a tricky one. I stepped on some of the landmines in this problem, so hopefully I will be able to avoid that on the future problems. I'll be back again tomorrow, assuming I actually solved the problem properly. Subscribe to a YouTube channel, subscribe to the Monday Morning Haskell mailing list using the link in the description. Hope you're enjoying these videos, hope you're learning from them, and like I said, I'll see you tomorrow.